In this deck, we focus on rail terminals as high-impact coordination nodes in the supply chain. A rail terminal is not just a place where trains stop. It is a synchronized operation where containers must be transferred quickly to trucks, placed into a yard, or loaded onto other trains. When schedules fail, trains dwell longer, tracks get blocked, and delays propagate into ports, factories, and distribution networks. The rail terminal scheduling problem is to decide in what order and with which cranes container handling tasks should be performed for arriving trains. The objective is to minimize overall completion time while meeting train departure commitments, respecting crane travel and capacity, and enforcing precedence requirements between tasks. Consider the Port of Hamburg rail terminal, which processes over 2.3 million 20-foot equivalent units annually. During peak hours, trains arrive every 15 minutes. Each train carries between 20 and 60 containers. Multiple rail-mounted gantry cranes must coordinate so trains can be processed fast without collisions or resource conflicts. A single poor decision can ripple into dozens of later decisions, causing expensive delays. The operational goal is to reduce train dwell time and keep throughput high, even when arrivals are dense. We solve the rail terminal scheduling problem through multiple tiers. Tier 1 builds a dynamic programming formulation to define the state, action space, and Bellman recursion. Tier 2 uses improvement-based local search to rapidly improve a feasible schedule using neighborhood moves. Tier 3 applies Tabu search to escape local optima with memory structures. Tier 4 uses an Ensemble learning framework to predict make span and recommend assignments with quantified uncertainty. Tier 5 embeds the system in a digital twin for uncertainty-aware scenario simulation. Tier 6 explores autonomous multi-agent negotiation. Tier 7 adds a human and artificial intelligence symbiotic partnership for high-stakes decisions. Tier 1 frames rail terminal scheduling as sequential decision-making with optimal substructure. At each stage, you choose which tasks each crane will execute next, given remaining tasks and current crane positions. The value of dynamic programming is correctness and interpretability. It provides a benchmark for smaller instances by evaluating the best possible future continuation from each state. The limitation is scaling, because the number of states grows quickly as the number of tasks increases. This slide defines the main sets: trains, cranes, container handling tasks, and decision stages. Operationally, these sets define what the scheduler is controlling. Tasks are the atomic pieces of work. Cranes are the constrained resources. Trains impose arrival and departure timing that creates urgency. Parameters include train arrival times and scheduled departure times. Each task has a processing time on its train. Cranes also have travel time between positions, and each crane has a capacity. A critical parameter class is precedence. Some tasks must be completed before other tasks are allowed to start. Operationally, precedence can reflect safety sequencing, access constraints, or required ordering in a train or stack. The dynamic programming state includes what tasks remain and where each crane is currently positioned. Operationally, this state is the minimum information needed to make the next decision without remembering the entire past. Remaining tasks define what still must be done. Crane positions define travel time and feasibility of the next assignment. This slide presents the Bellman recursion logic. From a given state, you consider feasible assignments of tasks to cranes. For each crane, you account for processing time and travel time from the crane's current position to the task position. The recursion takes a max across cranes to reflect parallel execution and uses a mine across actions to find the best decision. Operationally, this is the formal version of choose the next coordinated set of actions that leads to the shortest overall completion. The boundary condition states that when no tasks remain, the remaining completion time is 0. Operationally, this closes the recursion. It defines what done means: all tasks completed, no further work required. The objective is to minimize overall make span while respecting train departure constraints. Operationally, this means you want the entire set of required container moves completed as early as possible without causing any train to miss its departure time when those constraints are binding. This slide collects constraints such as departure feasibility and precedence. If a task must precede another task, the schedule must enforce that ordering. Operationally, constraints protect against two common failure modes: schedules that look fast but violate required order, and schedules that push work past a train's scheduled departure, creating network-level delay. This diagram visualizes the dynamic programming structure. Use it to connect the math to the story. State evolves over stages as tasks are completed, and crane positions update. The diagram emphasizes that decisions are sequential and path-dependent. This example includes two trains, two cranes, and four container tasks. Train 1 arrives at time 0 and must depart by time 25. Train 2 arrives at time 10 and must depart by time 40. Processing times are 8 minutes, 6 minutes, 10 minutes, and 7 minutes. There is a precedence requirement that task 1 must occur before task 2. The example shows how the first stage must assign task 1 due to precedence, and the final schedule achieves a make span of 33 minutes while satisfying the constraints. Tier 2 uses improvement-based local search. The idea is to start with any feasible schedule, then improve it by exploring neighborhoods of similar schedules. Neighborhoods include reordering tasks on a crane, reassigning tasks between cranes, and improving crane repositioning. Operationally, this gives fast improvements without requiring an exact solver. This diagram shows neighborhood exploration and iterative improvement. Operationally, it highlights a practical workflow. Propose a small change, evaluate whether makespan improves, accept the change if it helps, and repeat until no local improvement remains. In the first code section, you typically see how an initial feasible schedule is built and how makespan is computed. Operationally, having a correct evaluator is essential. If makespan evaluation is wrong, the search will optimize noise instead of true performance. This section usually implements neighborhood generation, such as swapping two tasks within a crane sequence. Operationally, swaps must respect precedence. If a swap violates ordering, it should be forbidden or heavily penalized. This section typically implements reassignment moves between cranes and evaluates the result. Operationally, reassignment is powerful because it can rebalance workload. It often yields the biggest gains when one crane is overloaded and another is idle or underutilized. This slide reports a concrete improvement trajectory. An initial schedule with makespan, 33 minutes improves to 29 minutes after a task reassignment. The method converges after 67 iterations with a final makespan of 27 minutes. That is a 12% improvement over the initial schedule. The operational message is that small, systematic changes can produce significant gains. Tier 3 uses Tabu search to escape local optima. Tabu search adds memory so the algorithm does not cycle between the same small set of schedules. Short-term Tabu lists forbid recently used moves. Intensification focuses search on promising move patterns. Diversification pushes the search into new regions when progress stalls. Operationally, this is designed for rugged landscapes with many traps. This slide highlights memory structures: short-term, medium-term, and long-term. Operationally, these memories balance two needs. You want to exploit what seems to work, but you also want to explore when the method gets stuck. This code section typically initializes a schedule, a Tabu list, and evaluation functions. Operationally, the Tabu list must be encoded in a way that meaningfully blocks cycles, such as banning specific swap moves or specific reassignments for a number of iterations. This section usually generates candidate moves and chooses the best allowed move. Operationally, the algorithm may accept a temporarily worse move to escape a local optimum, as long as the move is not Tabu or is allowed by an aspiration rule. This section often updates Tabu tenure and tracks best-known solutions. Operationally, adaptive tenure prevents the search from becoming too rigid or too permissive. It adjusts memory length based on progress. This section typically implements intensification and diversification logic. Operationally, intensification reuses successful patterns. Diversification forces exploration of new combinations of assignments and orderings to find breakthroughs. This slide reports a case with 4 trains, 3 cranes, and 12 tasks. Makespan improves from 52 minutes to 38 minutes after 1,247 iterations. Tabu tenure averages about 4.2 and adapts within a small range. Total improvement is 27% over the initial schedule. The operational lesson is that memory-guided search can systematically push past local traps. Tier 4 uses Ensemble learning to predict performance and recommend decisions. The system combines multiple models such as random forest, gradient boosting, support vector approaches, a neural network parameter tuner, and a meta-learner. Operationally, the goal is robust decision support. Instead of relying on one model that may fail under certain regimes, an ensemble can blend strengths and provide more reliable recommendations across diverse instances. This slide visualizes the ensemble structure. Different learners produce complementary signals, and a meta-learner blends them. Operationally, the meta-learner can weight models differently depending on instance features such as how dense arrivals are or how many precedence constraints exist. This code section typically handles feature extraction and dataset preparation. Operationally, features might include task processing times, crane travel distances, precedence density, and arrival spacing. Good features are critical for prediction accuracy. This section typically trains component models and performs validation. Operationally, validation is needed to avoid overconfidence. A model that performs well on historical data but poorly on new regimes can cause harmful scheduling recommendations. This section often implements the meta-learner that blends predictions. Operationally, blending helps handle model uncertainty. It can reduce variance and produce better calibrated recommendations. This section typically produces predictions and confidence intervals. Operationally, confidence intervals matter because they tell planners how much risk is associated with a schedule. In a high uncertainty situation, you may choose a more robust schedule instead of the most aggressive one. This slide reports training on 500 historical instances with optimal solutions. Random forest achieves 92.3% accuracy in make-span prediction, with mean absolute error 2.1 minutes. A test instance predicts 41.2 minutes versus an optimal 39.8 minutes, about 3.5% error. A reported confidence interval spans 38.9 to 43.5 minutes. The key point is that learning can guide scheduling with quantified uncertainty. Tier 5 introduces a system of systems digital twin. Sensors feed real-time analytics, discrete event simulation, and decision support. The twin continuously calibrates itself from real-world events and uses Monte Carlo simulation to evaluate uncertainty in arrivals, breakdowns, and weather impacts. Operationally, this enables what-if analysis and proactive response planning. This slide presents the data-to-decision pipeline: sensing, simulation, optimization, and recommendations. Operationally, the architecture ensures that the schedule is grounded in real-time conditions, not static assumptions. This slide highlights uncertainty sources such as arrival noise, crane breakdowns, and weather. Operationally, uncertainty is the reason static schedules fail. A robust scheduling system must explicitly model these disruptions. This slide reports Hamburg digital twin metrics: 2,847 containers per day across 23 tracks with 8 cranes. Real-time sensors update train arrivals every 15 seconds with 99.7% accuracy. The twin runs 1,000 Monte Carlo simulations per planning horizon. Reported what-if results include a 23% throughput increase from adding a fourth crane with an investment of 2.1 million euros. Disruption response reduces average delay from 47 minutes to 23 minutes. Tier 6 reframes the terminal as an agent ecosystem. Train agents bid for service based on delay costs, crane agents bid for tasks, and infrastructure agents manage track conflicts. A market maker agent enforces stability and fairness. Operationally, this enables coordination without a single centralized scheduler and can improve resilience when disruptions occur. This slide shows negotiation and coordination without central planning. Operationally, the architecture focuses on message passing, bidding, allocation, and enforcement, so decisions emerge from local interactions. This slide introduces a fairness metric, emphasizing that efficiency is not the only goal. Operationally, fairness matters because repeated disadvantage to certain trains or operators can cause service failures, contract conflict, or political pressure. This slide reports equilibrium outcomes. Average make span is 34.2 minutes versus 39.1 under centralized control. Throughput increases by 22%, and system uptime reaches 99.7%. A fairness index of 0.94 indicates near-perfect fairness. The system adapts automatically to 89% of disruption scenarios. Tier 7 uses a Centaur model that blends human judgment with artificial intelligence optimization. The system provides explainable recommendations with confidence intervals, while humans add context and value-based decisions. Interfaces can include natural language explanations, augmented reality displays, and predictive analytics. Operationally, this is designed for high-stakes environments where pure automation or pure human control each has weaknesses. This slide describes the collaborative workflow: planning, optimization, evaluation, and learning. Operationally, the learning loop is important. The system should improve as it observes outcomes and as it learns from human overrides and expert patterns. This slide presents a crisis scenario: a crane failure during peak operations with 8 trains waiting. Artificial intelligence proposes redistributing 14 tasks with a predicted delay of 23 minutes and offers alternatives. Humans consider morale, customer relationships, and inspection risk. Reported response times are human only 8.3 minutes, artificial intelligence only 0.7 minutes, and symbiotic 2.1 minutes. Reported performance improves 31% over human only and 18% over artificial intelligence only. These practice questions reinforce modeling and implementation. You formulate a dynamic programming model for 2 trains and solve the optimal make span. You implement local search neighborhoods and identify best improvements. Design Tabu search with tenure 5. Describe Ensemble feature engineering and meta-learning with confidence intervals. Specify digital twin integration points. Analyze Nash equilibrium for bidding agents. And design a human and artificial intelligence crisis framework. To close, rail terminal scheduling couples trains, tasks, crane travel, and precedence. Dynamic programming formalizes optimal substructure but scales poorly. Local search and Tabu search provide scalable improvement and escape local optima. Ensemble learning can predict and guide schedules with quantified uncertainty. Digital twins and multi-agent systems improve resilience under uncertainty. Human and artificial intelligence symbiosis delivers better decisions in crises than either alone.